Our next presenter is Volodymyr Kyrylov from the Swiss Italian University.
Hi everybody, my name is Vol. I'm a student at UZI, and I'm really happy to share this ongoing work that I'm doing at UZI as part of my master thesis and my master program on accelerated scan for compressive language models. So my login is darkproger. This is how you can find me online. Before I started my master's, I saw this paper called Language Models for Few-Shot Learners, which was super hyped. And before that, there was a paper called Language Models for Unsupervised Multitask Learners. And the cool part about this paper is that OpenAI claimed they trained an amazing language model that generates all kinds of text, but you cannot get it. I was really pissed about that. And I was pissed for about 2 months until they actually released it, so everybody could see that it's not actually that good and there's nothing to worry about. But I was really interested in the capabilities that you could find inside the model so you can amplify them and maybe get something interesting with it. So this particular model, GPT-3, was interesting because you could make it learn new things at test time. So after you're finished training, you can put in new examples and have it learn a new task from just those examples. That was pretty mind-blowing, so I decided to figure out how this works. And when I started my master's in the first year, we used the UZI cluster to train a language model for Ukrainian. We gathered all kinds of data in just pure Ukrainian and trained the language model to do well, essentially what it does, to compress the text. So we released a language model by training for about 4 weeks on a single 800 for a month, right? And we got the state-of-the-art performance and on training on Ukrainian from scratch and evaluating on this Brook corpus, which is like a pen tree bank if you're into NLP for Ukrainian. So with this, I was really glad to see that thanks to the recent developments of software, you can train GPT-11 model on consumer, basically, hardware. So we even reported the numbers on how much hours it takes to reproduce this result, so more researchers can go in and train their own models. This was partly possible, and like 1.5 years ago, there was a release of PyTorch 2.0 beta, which has this really cool feature called compile. It would look at your code, and then it would see sequences of different runs of CUDA kernels, and then it would generate new code that runs all of those kernels together, so you don't have to pay the overhead of finishing kernel, reading in a line of Python, then launching a new kernel, and then reading it again. And along with that came this amazing library called Flash Attention. And what Flash Attention allowed to do is that it showed to everybody that you can compute this attention computation, which is an interaction between all the input words, pairwise, in constant memory. So before that, you would have to allocate this massive attention matrix on your GPU, and then use it to compute all of the values. But this particular implementation showed that not only there's an efficient algorithm that does it in constant memory, you can also do it really fast on the GPU. So these two particular advancements allowed us to do work like training GPT-2 from scratch on Ukrainian. So I have this library online. You can pip install it and try it yourself. And the interesting thing that we did is that we tried to format the data in a way such that you take your document and then you prefix it with metadata, and then you put the same copy of the metadata at the bottom. So because the training data was formatted this way, it allowed us to perform metadata condition text generation. So I give you a title, you give me an article, and I give you an article and you give me the metadata. So you can do both generative tasks and discriminative tasks, so to speak, at the same time. And what I really liked about it, so this was meant to be video, but if I prompt it with a sequence of digits, it starts counting up to 100. So that was pretty cool. I thought, well, you don't just learn, maybe you just learn counting by just looking at the training data. Somebody counted to 100 in the training data. And I checked, And because the data is crawled from the internet, there are mostly like page numbers, but the page numbers only go from like 1 to 20, or like from 80 to 80 to 100, but they are not joined together. So the model learns to interpolate different training data all by itself, which was pretty amazing. Right, oh yeah, there's the video. So you type in the prompt, and then it just generates a continuation for you, which is based on interpolating the training data. So because I don't have massive compute, I have to enjoy these little things that the model does, because I need to otherwise scale it up to like 500 billion parameters to see something really amazing. So I have to pay attention to these little things that the model does to interpret its behavior and seek ways to amplify it. So the model, like if you train a GPT-2 level model, doesn't do few shot learning on the level that you're used to. You just give it like a bunch of in-context examples and figures out the task. But it does these little things. So this is a real string from Wikipedia, 42, space, 16, space, 26, space, 22. So just like a long, boring string. And what I asked the model to do is I asked it to assign a score to every token in the sequence. And generally, if you look at the pattern, the scores kind of decrease over time, which means the probability of the input increases, meaning the model gets more confident in what's going to happen next. But there was an interesting pattern there. If you look at the end, there's a sequence that goes like 21, 23, 4, 17, 20, 31. And if I look at the score, right about where the space happens after the 4, there's a score of 312. That's a massive score compared to everything else. So the few-shot learning behavior in this model is that it has learned to count the numbers of digits, and then expect a space after the 2 of them. And that because that space was unexpected, it assigned a high score to it, and that's few-shot learning. All right, all of this is possible by just predicting a single training objective called predicting the next word. So you can do a text condition prediction and metadata condition generation. But what I decided to try to do with this model is that I tried to extend it to other NLP tasks, which are not usually done in this instruction setting. Like in ChatGPT, everybody's used now that you type in things and then it gives you like a continuation. But before in NLP, you would do these so-called parallel tasks in which you input a sequence of words, and then it gives you a parallel output sequence of these word tags. For example, for named entity recognition, where somebody's scanning a news article, they want to highlight all the names. So the model would see all of the words in parallel and then output all the tags in parallel. So that would be for named entity recognition, the tag would be /p/p/p for a particular substring where there's a name. Right? So, but if I try to train a small model to complete this task, I would see that if I give it longer sentences, it starts forgetting what kind of tasks it's doing. So it just gives me part of the output, but then it seems to just repeat itself to somehow minimize its loss or increase probability of the output, so the model feels happy and confident about what it's doing, but it actually cannot properly complete the task. To improve this behavior, what I would need to do as a machine learning engineer is I need to find more data that has this distribution property that I care about and amplify this data in the training set. Or I can figure out some tricks how to make the existing model do something until completion by me guiding the model to help it. For example, in this particular case, I would help the model by reminding what exact word it's supposed to be processing, which is sort of what a parallel model already does out of the box by construction. So I thought, to amplify the data, I can use the GPT I've just trained to generate more data for the GPT, right? That seems simple. Everybody likes synthetic data. We can generate billions of tokens and just put it in the model again. So the problem with doing that is that actually when you train a GPT model, or like another regressive language model, the cost of training the model is much less than the cost of inference, particularly because when you're training a model, you can backpropagate signal for training for all tokens at the same time, but when you're generating text, you can only generate one token at a time. So you have to run the whole model with the whole context over and over again. So here, to illustrate this, I want to show you a concept from a part of the transformer that's called the self-attention block. And in the self-attention block, you have these queries, which is your input, the input for your last token, and you have keys and values, which is a history of representation that's accumulated over the course of the whole string that your transformer is generating. Right? So every time I generate a new token, I have to put the token I've computed my representations for into the key value cache, generate one more token, put more representation into the key value cache, and it keeps going on and on. So this thing is growing proportionally to your input. So if you're generating a massive prompt in ChatGPT and you keep looking at it, you can see that over time it starts generating slower. And that's because for every new token, it has to look at all the key value cache to figure out what it has to do next. Moreover, because your transformer is a very deep neural network, it does the same thing about 100 times. So there are 100 key value caches for 100 layers in the GPT-3 or GPT-4 transformer, because those networks are really deep. So there's a lot of memory that your GPU is storing just to represent the past words that it has seen or generated. So just a little bit of algebra so you can see the problem algebraically. This is the definition of attention that the original authors use in the 2017 paper. But I like to use this kind of definition in which you can see that in this MATLAB-like notation, you're just appending a vector of keys and values onto the matrix called A, and then you're doing a key value, a query on top of it. So this thing, you're just like, in MATLAB, you're just appending to the end of the array. That's like what it's doing during generation. And for example, if you're caring about long context tasks, this is very important. Like if you want to get a job as a machine learning engineer doing transformers, everybody wants to get long context. So what they have to do to get long context training, they have to set up training in a way such that if your string is like 1 million tokens, it's not going to fit on a single GPU. It's probably not going to fit onto a single node. And moreover, when you're having to compute attention, your query needs to look at every single key value in that string. So what they do, they make a ring out of computers, and then they set up your queries, and they scroll keys and values all over the ring, so every key and value has to visit every node for every token. That's super inefficient. That has quadratic complexity in time. Well, as we've seen, it no longer has quadratic complexity in space, but it's still super expensive to do this. Right. So how do we generate and spend constant memory by accumulating this key value cache more efficiently, right? So when we're computing the attention memory, we no longer have to generate this large attention matrix, but we still have to keep these key and values in memory, and that's where the quadratic time complexity comes from. So when we were working on the GPT-2 paper, we trained this model called LSTM. It was super small, but it was performing surprisingly okay on this bits per character compression metric that we were measuring. So we decided to look into it a little bit deeper. So technically, ITSIA, the lab, the AI lab that's hosted with our university, is the place where all of the recurrent neural network stuff has happened in the 90s and in the early 2000s, and that's how like recurrent neural networks have been dominating before transformers. So choosing Uzi to come to become a student was a great decision for me, and I'm really happy about that, so I can learn all about recurrent neural networks. So what a recurrent neural network does is it takes your input token U, it somehow projects it, and then it adds to a version of your hidden state. So this X is your hidden state. It adds these two representations together and makes a nonlinearity. It performs some kind of control flow-like operation. You can think of it as like looking at your state and then making a decision based on your state to do something else. So the nonlinearity is something like an if. Like you can think of it like that. So in this particular situation, what this model does is it looks at every input token, accumulates it into a fixed amount of memory, X, and then makes a nonlinear decision. So in here, what's happening is that the model kind of accumulates this blue state over time. And this blue state, this changing its color, has fixed amount of memory. It uses fixed amount of memory, and it doesn't grow with your sequence length. So on top of the recurrent neural networks, there was work on long short-term memory, which extended this construction to solve a problem that when you're trying to train this kind of network, it's really hard to backpropagate this information because this kind of vector has really dark color, and like there's a lot of information in there. You don't know what contributed to accumulation of this particular information in this vector at this point in time. So this long short-term memory was made to address this problem of I don't know where this input came from by inserting this gating mechanism. So I think of it as like a memory controller that over time, what it first does is it chooses what to write to memory using this thing called I. It's an input gate. And it also chooses what to remove from memory using this gate called F. So this is a forget gate. So they extended the recurrent neural network with a dynamic memory controller. Like it performs decisions of what kind of things are relevant to this particular point in time. And it also has an effect that it helps the network figure out where this input came from during backpropagation. So it also solves the problem of training this efficiently. And however, the thing with having a network that performs these nonlinear decisions at every point in time is that you cannot train this in parallel, because you have to take an if, then figure out where you ended up, and then do something else. You have to do all of these steps sequentially, and this is the reason why LSTMs came out of fashion for the recent 6 or 7 years. But besides that, they're quite great. They do memory management automatically. They generate really fast, so it would be really nice to use them, especially in smaller systems. So I was really inspired to fix that, and I noticed a project by Immanuel Schlag at ETH called the Linguini Kitchen, and he introduced this model called quasi-LSTM, which uses a simplified construction of LSTM that enables parallel training. I'll show you in a bit. And he shows that if you try to train GPT and QLSTM side by side, the QLSTM looks worse, but if you extrapolate, it actually gets better later over time. So the intuition behind that is that if the learner learns to compress its input, it's probably going to learn faster eventually because it's spent all of the early time learning to compress the input, which self-attention already had access to from the get-go. So this quasi-LSTM make a small change that it removed this dependency on the past output, so it made this particular equation parallel because this thing is now associative. So Immanuel made this interesting construction in this paper that says, oh, you can construct this forget matrix, and then if you perform matrix multiply, this can be done in parallel because NVIDIA GPUs can do matrix multiplications really efficiently, and then you get your language model. The problem with this is that transferring these kind of matrices that you assemble for the whole, in this case, it takes n squared memory, where n is your sequence length. It takes a lot of time on the GPU. So I joined ETH for my exchange semester in the past 6 months to do this project on scalable recurrence, where I thought, oh, don't actually have to compute this matrix and then send it to GPU. You can send a program to the GPU to compute that matrix in place. And this was enabled by this particular paper from 1990s called Prefix Sums and Their Applications. So it based on this really simple idea that associative expressions don't care from which side you compute them. So if you're computing a sum, you can compute the left end of the sum, or you can compute the right end of the sum first and then combine them together. Because of this, you can compute parts of the sum independently and make this computation that looks like a tree. But if you want to compute a cumulative sum, after you're doing this sweep of computations, and here I show it down, from leaves to the root of the tree that's at the bottom, you have to use the next sweep of the computation to push the data forward by a little bit. And this algorithm is what Guy Blelek proposed and showed that you can apply them for any mathematical expression in which this black dot is an associative operation. So now, we have to figure out what other mathematical operations have this associative property except the plus and multiplication, which are like very known examples. So, right, and yeah, if you plug them together, the computation looks like this. It's going to be interesting a little bit later. Right, so he in his paper, he actually defined this operation that acts on this CIB circle cross, and this looks a lot like this particular recurrence that we use in the quasi-LCM. So this particular definition of an associative operation enables to compute recurrence for quasi-LSTM in parallel, and that was pretty amazing, and I applied this, and this basically was the project. Right, so if I implement this particular recurrence in PyTorch, what I ended up having is that I'm actually faster than the self-attention operation, in which the memory consumption is quadratic, but I'm still slower than the flash attention, this optimized implementation of attention from TreeDAO. So I'm roughly in between, even though my algorithm is asymptotically better than the self-attention. So my n-log-n algorithm works slower than the super optimized square algorithm for self-attention. That was weird, so we had to fix this. Right, so I was not really focusing on performance improvements for graphing at the time. I was really interested if I try all kinds of competing linear recurrent neural networks, can I get it to perform on par with the GPT? And the answer was yes, I could make my model better up to tuning, so that was really promising. Right. Around the same time, there was a work from Albert Gu in TreeDAO, so the same TreeDAO who wrote Flash Attention on Mamba. And what they did is that they showed this interesting task called selective copying that showed why all the other linear RNNs that existed before didn't work really well in text, which was the reason why people didn't use linear RNNs for language modeling. And they've shown that if your task is to read a bunch of text and then repeat only some of it, this linear RNN cannot do it. It has a really hard time doing that. And they've shown that if you reduce this to a task in which you have to kind of copy text selectively, you can show that these old linear RNNs do not work. But the one that has automatic memory management control, in which it decides what to keep in memory and what to remove, handles it out of the box. So what they figured out is they figured out the same construction for their model called Mamba than we had in QLSTM, because we borrowed it from LSTM that was made in 1997. So it looks like the kind of science of RNNs is converging on a single point, that actually automatic memory management is really important, even for completing tasks as simple as copying data while ignoring some of the input. Right. And what TreeDAO did, along with the paper release, is they wrote a CUDA kernel that uses a recurrence that's very similar to ours, but slightly different. And what I did, I kind of patched out the things that I cared about to see if I can use their kernel for QLSTM, and I realized that I could actually match the performance of flash attention, but not exceed it. Okay. So a few months later, it led me to writing this particular library called Accelerated Scan, which is an implementation of this BLELEX parallel scan algorithm for NVIDIA GPUs, which kind of required me to learn a little bit of what GPUs look like inside. And what I learned was quite interesting. So first of all, this associativity, because it has these tree-shaped constructions, and in the associative operation, it doesn't matter what is like the shape of the tree. Does it have like 16 leaves? Does it have 32 leaves? It's up to me. So the width of this leaf is kind of dictated by the amount of memory this particular stage of the computation is having. So on an NVIDIA GPU, I was testing this, developing this on Ampere, a 3090 GPU. It's a GPU which has a few levels of the memory hierarchy, and on one of them, it provides this interesting instruction called the warp shuffle, in which it says, oh, so you have like a group of 32 threads. They all run on the same SM, which is a streaming multiprocessor, so we're gonna ask you for a direction and then we're going to exchange registers between threads in that direction. So that's an instruction called the shuffle, and that's what kind of drives operations on tensor cores, and that's what I use to speed up this algorithm. So here's that chart of the algorithm that I promised. So I could lay out the shape of the tree for this associative recurrence in a way that aligns with the structure of my particular GPU. So some of the data I put in the registers and did like a little bit of looping using vectorized instructions in them. Some of the data were exchanged using these warp shuffles, and they were exchanging data in this shared memory that kind of is one level above these registers. And then everything that didn't fit into one SM or into the shared memory, they were using GPU's global memory. So what one particular interesting issue I had with the algorithm when I was implementing about it is that when I have to do a backward pass, I have to backpropagate information from the end of the string to the beginning to compute the backward. I thought it's really weird because to backpropagate, I need to put the information, I need to start backpropagating from the last character right in the beginning. And that was kind of blocking me of claiming that my algorithm had like planetary scale because, well, if I run like half of the sequence on one planet and like half of the sequence on the other planet, and they're gonna exchange compressed information, then I have to like travel from the end of the string to the beginning of the string, like and send it like from Mars to Earth, and I cannot like just send the compressed stuff. But so this planetary analogy is maybe like actually applies to multiple computers in a cluster. But what I heard at this conference is that you can actually make these like toroidal topologies. You can connect just the last computer in the sequence to the first one directly using a cable, and that's pretty cool. It kind of relaxes the way how we can think about designing algorithms now, because you just can put cables everywhere. So that's my main highlight. Right, so I had to implement 3 ways of writing this algorithm for different libraries, each with a different way of hackability. And since I have 5 more minutes, I'm gonna speed up a little bit. I'm just gonna note that, and if you're interested in reasons why to write a CUDA kernel and you're a Python programmer, so here this purple curve is the speed of a scan implemented in pure torch with respect to the sequence length. And you can see that it kind of scales up, which is good, but there's this kind of curve in the middle that looks like a line, and this is what you get when you implement a for loop in CUDA instead of Python. So for loops in Python are really slow, but they're really fast in CUDA. So if you have short sequences, but you only care about performing really okay on the short sequences, you can just rewrite a for loop from CUDA to Python and get from Python to CUDA and get a really nice speed up. Right. But if you want to get an order of magnitude speed up on top of that, you need to use all the things that the GPU gives you. And that's what I'm going to say for now about this. Right, so so far it sounds all too good to be true, but is linear recurrence enough? That's like the next question you kind of ask once you're done implementing all these algorithms. And it turns out, so the difference that's shown in this paper is roughly like this. In a transformer, you can paste a bunch of text into the prompt and then ask a question. But if you do this with an RNN, the RNN, because it's compressing, it doesn't know what to compress. Usually, if you do this with an RNN, it doesn't know what to do. So to make an RNN work better, you first have to ask a question and then paste the context. This way, it will know what to compress, and it's going to work better. So technically, if you have a workloads that don't work like that, linear recurrence will not be enough. And that's why people start mixing transformer layers, so self-attention with recurrence. And this is what recurrent gamma has done. And the architecture they use is called Griffin. And accelerated scan is currently the only kernel that can support parallel training for Griffin on the GPU, which is pretty cool. Yeah, so that's what it looks like. But it's just like a mix of transformer and recurrence layers. Right, and this is a very interesting topic to work on right now because the developments are happening on a daily basis. So one particular idea that was presented in HGRN2 is an idea that was called in the 90s the fast-weight programmers. And the difference from RNNs is that now having a vector-valued state, you have a matrix-valued state, so you can have more redundancy when storing your representations, and it actually makes learning faster in some situations. Like on some synthetic benchmarks, you get 10 times faster learning because there's less stuff to compress in the beginning. That's pretty cool, but it kind of shows a trend that recurrence tries to make the hidden state roughly proportional to the sequence length, so it looks a lot like transformers. So kind of in this stage of development, it's weird that the transformers are seeking ways how to make the sequence length shorter and inventing these like feedback memories and stuff. And in recurrence, you see they're actually expanding their state to be more like transformers. So it's a place where we're like looking for an equilibrium point. Right, so to sum up, LSTMs were slow to train, but if you make them linear, you can train them in parallel over the sequence length. And this gives you generation and constant memory, so now you can do all the things that you might want to do when you want to massively generate data using a GPD and then use your whatever conditioning technique you want to improve the generation quality. So yeah, to get some confirmation bias, there was a talk at a panel from transformer creators at the NVIDIA conference, and they said, well, the world needs something better than transformers, and that's probably going back to nonlinear recurrence over sequence length, because you can actually do more stuff. But to do more stuff, you need to do it in parallel. So a linear recurrence is a way to kind of get the best of the both worlds. Yeah, that's like a comment from yesterday. So Kyung-Hyun Cho is the author of GRU, and he's really happy that the LLM people are rediscovering that nonlinearities are cool over the sequence length because they let you do more stuff. So that's an interesting development that's happening right now. And yeah, that's it. I'm really happy to share my work with you, and I learned a lot from you how to better put my programs onto your computers, and thank you very much.